This lecture is about optimization. So we have found min and maxes on a bunch of different formulas and functions, and now it's time to basically take words, transform them into functions, and then find the min and max as needed. Okay, so this is called optimization. We're not going to get too bogged down into optimization here because we can't really do that much that's very interesting in two variables, so we're just going to do some basic examples so that we know that it's out there and we can use it. It's really much more useful when we start getting into multivariable calculus, which is technically our Calc 3 here. Okay, so a rectangular garden is to be constructed using the side of a garage as one side and wire fencing on the other three sides. Given 150 feet of fence, find the dimensions that would create a garden of maximum area. Okay, so we have some instructions here. Okay, so the first one is that we always draw a picture whenever we can. Okay, so I'm not an artist by any stretch of the imagination, so I'm just going to write that we have the garage here, and then my picture looks like this. Okay, so we're butting the fence up against the garage so we don't have to put fence on that side. Okay, so we have that picture, and now we know that we have a couple of different things. We know that we're given 150 feet of fence, and we know that we want to create a garden of maximum area, okay? So this is the thing, the said that maximizing is we want to maximize the area. So let's label. Okay, so I'm just going to call this side X and this side Y. It said it's rectangular, so I can assume that they're different. And so I could just put another X over here because rectangular means that these two sides are the same, and then these two sides would also be the same. All right, so based upon the fact that we know that we want our maximum to be area, so this is the formula, right? The thing that says maximum, this is the thing we're going to do all the calculus on, okay? So that is our primary equation. It says determine the primary equation, the thing we are optimizing, which in this case is area. So from my picture, I have X times Y, okay? All right, so now we need to write a secondary equation relating the variables if needed. So this is needed when the primary equation has more than one variable, okay? So the secondary equation must be something to do with the 150 feet of fence. Okay, so when I put fence up around something, that's really goes around the perimeter. So I know that if I look at this picture, the perimeter is just the sum of all the sides, so that would be 2x plus y, and I have 150 feet of fence, okay? So this is my secondary equation, okay? Now just a hint here, when the thing that I'm going to optimize, I never know what it's equal to, ever. Okay, so this thing that I know what it's equal to, I know that that's not the one I'm going to do calculus on. Because if I knew what it was equal to, I wouldn't be doing the optimization, right? So I'm just writing a formula for the maximum, or for basically the area. And then this formula here is going to help me so that I can get rid of one of these variables. So the easiest one to solve for here is y. It doesn't matter which one you solve for. I always go usually with the algebraically more simple one, and if I have a choice, I always solve for y because I tend to start writing x instead of y when I try to use y. So I'm going to solve for y. So my y is 150 minus 2x. Okay, so now the next part is to write the primary equation. So this is number 4. So we've drawn the picture, we've determined a primary equation, we've written a secondary equation, and then we're going to write the primary equation in one variable if it wasn't already, using the second equation. So if we have the secondary equation, now we're going to so this is the thing we want to do all the calculus with, but we don't know how to do multivariable calculus, so I need one variable. So basically I'm going to write this as my a of x function, so area. Okay, this is the thing I'm trying to maximize, and that would be x times, and now my y here, I'm going to substitute in as 150 minus 2x. Okay, so now before we move on to actually doing the calculus part, there's one last thing that we need to consider. Okay, so we want to identify the domain using the secondary equation. So we're going to use a combination of this and this to figure out our domain. So our function is in terms of x. So technically, right, I mean, really, like the smallest side, we can't really use 0. So we'll say we're on the open interval at 0 because each side should be bigger than 0, right? So technically x should be greater than 0 and y should be greater than 0 here. And then also, the other thing I need to consider, so this is between x and x, right? These are what it's valid for. So I know that x and y both have to be bigger than 0. And this is my y here, which is 150 minus 2x. And when it is 0, right, then x is 75. So basically the biggest possible x value that I could use is 75 here. Because if I plug in 75, and really I shouldn't use that one, because I'd get 150 minus 150, and then my y side would be 0. And then my area would be 0, because whenever I multiply by something by 0, I'm going to get 0. So technically speaking, my domain restriction here is between x is 0 and x is 75. Now I know that these endpoints aren't included, but if I include them, then I can use that the thing that we learned earlier that basically said that if I am on a closed interval, then I know for sure I'm guaranteed a min and a max. So I'm just going to pretend like I can use 0 and 75. So I'm just going to say that this is a closed interval. Okay. Now I can do this because of the addition, like this is addition and things. Sometimes I can't always do this. But like if I just can't use the 0 and I can't use the 75, then I'm just going to be like, yeah, I'm just going to sneak that in. Okay. All right. So my a prime here then of x is, actually, let me multiply through here. So my rewrite a of x is 150x minus 2x squared. And then to optimize or find the min and the max of anything, I am going to find the derivative of that, which is 150 minus 4x. Okay, so if I set this equal to 0, because that's always where my mins and max happen, I get 4x equals 150. And so my x will be, let's see, what, 3750? Okay, so essentially that is going to be the side. So that's the one side. So basically I'm going to have two sides that are 3750, and then to figure out what y is, I will put that in. So then I come back to here because I want the full dimension. So I know that one side is 37.5, and then we were in meters, I think. No, we were in feet, okay. So one side is 37.5 feet, and then I come back to my secondary equation that I have all solved for y. I pop in my x, and that tells me that y is equal to 150 minus 2 times 37.5, which ends up being 150 minus 75, which is 75. So I end up with my dimensions as x equals 37.5 feet by 75 feet. All right, now, since I'm technically on a closed interval, then I can pop in my endpoints, but I notice that when I plug in the 0, my area will be 0. And when I plug in the 75 here, I get 0 times x. So my areas on the endpoints are going to be 0. So this definitely has to be where my maximum comes from. And if I wanted to know what the maximum area would be, then that would be, so that would just be x times y, right? So that would just be 37.5 times 75 feet, and that whatever I end up there is going to be in feet squared. Okay, so that I wasn't asked that question. I just wanted the dimensions that would create a garden of maximum area. But if I wanted to know how many square feet were in my garden, I would then just multiply my two things, which I didn't do in advance, and I don't have a calculator handy, so I'm just going to leave that to you. Okay. All right. So another type of problem. Now this one is a little bit easier. So we have the revenue of a company producing X items, which is given by R of X is equal to 100X. The cost of producing these x items is given by C of x equals 30x plus x squared. We want to know how many items should the company sell to maximize profit. Okay, so this time I don't need to figure out any formulas. It's all, well, I do have to do a little bit of work here. So anybody who's taken economics before will remember that the profit, P of x, is equal to the revenue minus the cost. So I just have to be careful with my signs here. So I do have to make my profit formula, but not like the other one where I had to come up with my own formula. I mean, I have the two formulas. All I need to do is subtract them. So P of x is 100x, and then minus, then my C, the whole thing gets subtracted. So 30x plus x squared. And when I distribute through there, my P of x is going to be 100x minus 30x minus x squared. So I can do a little bit more condensing before I do the derivative here, because I have like terms here. So I have 70x minus x squared. All right. So I'm trying to maximize the profit, right? So I have that. It's all in one variable, so I don't even need to really draw a picture or anything. So this is like the dream case. So now I just need P prime of x, and that would be, so the same thing happened on the last one, but I don't have a closed interval here. I'm not really sure. I know that x should be greater than 0 because I've never heard of a place that produced negative items, right? So I know that for sure x has to be positive, and I'm hoping that my profit is also positive, but I'm really considering, I don't really have a closed interval in this case, but since my profit function is a quadratic with a negative leading coefficient, that means it'll look like this. So I know it's going to have a maximum point, okay? So my P prime of x is 70 minus 2x, and if I set this equal to 0, I find out that x equals 35, so is my maximum quantity that I should produce. So basically I should be producing 35 items to maximize my profit. Now if I want to know what my max profit is, then I plug in my 35, I do P of 35, and then that will give me my maximum profit. I didn't really say what my profit was in, whether it was in thousands or hundreds, but I didn't really say what anything was in, but if I wanted that detail, I would give it to you. Okay, so let's do another one. Now this is a little bit different take on the first one that we did. So this time we have a farmer planning to fence a rectangular pasture adjacent to a river. So this time instead of a brick wall, we have a river, okay? So this is my high class drawing skills, right? So there's my river, and I want a rectangular pasture that's going to butt up to it, okay? So instead of a fence on that side, I'm going to use the river. Apparently the river is deep enough that whatever my herd is not going to cross it. And I need the pasture to contain 245,000 square meters to provide enough grass for the herd. So what dimensions should the farmer use if they want to minimize the amount of fencing used? Because fencing is expensive, so we want to use the least amount of fence, but still maintain our square footage here. Okay, so we know that my pasture should contain 245,000 square meters. Square meters tells me that that is the area. So again, I'm just going to label these. It doesn't matter if I call this side Y and this side X. As long as you label them and keep them labeled correctly, then you come up with the same answers, okay? So if this is area, then the area of this rectangle, now I'm going to, I am going to think of this as a rectangle, so maybe my stream is a little bit straighter on this side. So my area, XY, is equal to 245,000, right? This is my secondary equation because I know what it's equal to, so I know for sure it's not the thing I'm optimizing. And we want to minimize the amount of fence, so that's the one I'm going to do my calculus on. So fencing is perimeter, right? So perimeter, I'm going to call it F for my fencing, is 2x plus y. So again, I have mixed variables, right? So in this case, I have x times y equals 245. It doesn't really matter which one I substitute in. I'm just going to solve for y and get y equals 245,000 divided by x. Now in this particular case, right, I know that like if I try to look at my domain restriction and try to close off my interval, I can't in this case, right? Because I know that my x has to be bigger than 0. I know that my y should also be bigger than 0. And I can't, so in the other one, my secondary equation had a plus between it, right? So no matter how big I make x, I can just make y very small, right? So there's, on this case, we're really optimizing on the open interval from 0 to infinity. There's just not really a way to kind of close it off in this case. Okay, so here's my y equals. So now I want to come back to this. This is the one I want to do my calculus on, but I don't want to use it in two variables, so I'm going to substitute in this for my y. So I'm going to call this my f of x, f, capital F, meaning fence. So I have 2x plus, and then I have 245,000. I apologize in advance if I drop a 0. That's a lot of zeros, okay? So then I'm going to need my f prime. I'm going to do a quick rewrite of f before I do that. So this is 2x and then plus 245,000 x to the minus 1. Now the good thing I guess about these is once you get the optimization part, the calculus isn't too terribly difficult on the ones that we're doing at least. So my f prime of x is 2, and then my derivative here will be minus 245,000 x to the minus 2, which I really want to think of it as in terms with the positive exponent. So that's 2 minus 245,000 over x squared. And I want to make sure I get that minus sign or else I'm going to have some bad things happen here. Okay, so then I'm going to set this equal to 0. I get 2 minus 245,000 over x squared. And now I want to, I'm going to move the 245,000 over x squared to the other side, so it is also positive. So that would leave me with 245,000 over x squared equals 2. And now I can multiply both sides by the x squared. So I get 245,000 equals 2x squared, right? And now I have, if I divide this by 2, I get x squared equals 122,500. And then I'm just going to take the square root of this. I'm not going to put plus and minus in this case because I know that my side is a positive value, and the square root of 122,500 is very nicely 350. Okay, and so actually this one was in meters, so my x side is 350 meters. Okay, so now I need to figure out what my y is. So I want the dimensions of the fence. So right now I know that it's going to be 350 on these two sides, right? And so then my y, I know my y will be part of this. So I'm going to pull out this. So I have y equals 245,000. This is my original secondary equation. And I'm just going to put in my x. So I found that this was 350. And this one comes out really beautifully as 700. Okay? So now if you had your x and your y switched, right, if you had these y's and this is x, then you would have gotten y equals 350 and x would be 700. But regardless, the dimensions are 350 by 700. So my dimensions, all right, so basically I have 700 meters by 350 meters. And that's my optimizing. Now, if I was really worried that maybe this, I don't want to like minimize my fence and think, oh, by accident I got the max. So since I'm on an open interval, I can think of, right, so basically 350 was my x value. So that was kind of like my critical number, right, when I set the derivative equal to 0. So I got 350 out of it initially. And so if I wanted to, I could check on both sides the sign of my derivative. So if I plug in something like, I'm going to choose something really small, like x equals 1, because when I do that, I get 2 minus 245,000 over 1, which is definitely going to be negative. So I know that this is decreasing on this side. And then if I plug in something bigger, let's say I have x equals, I don't know, I'll just go with 500. So then in that case, I would have 2 minus 245,000 divided by 500 squared, which would be 250,000 possibly. I think that's the right amount of zeros. So this is actually going to be smaller than 1, so this is going to be positive. And so that means that I will have, in fact, a local min there. Right, so just remembering the first derivative test. Okay, so just in case, you don't want to optimize something and come out with something that makes it cost the most instead of cost the least.